So, today's topic is hashing. So I'm pretty sure many of you guys are very familiar with what it is. But just to have very strong basis, we are gonna go over some trivial information as well. But in the end, like, you will have a complete understanding of hashing, why we need it, and how useful it can be. And after that, you will have a homework, which is understanding the implementation mechanism of maps and sets in your preferred language. Because there are different alternatives. Like if we are talking about C++, there are ordered maps and unordered maps. And ordered maps, they work in a log n complexity, and unordered maps works in constant time. So it's important to know these minor changes in your language so that when you are using them in the interview, if your interviewer is knowledgeable of your language, like, because they would know all these tiny differences. And like, you don't want to get bitten by not having that information. It's very simple thing, and you guys are using these data structures very often. I mean, I guess you already used multiple times in your previous solutions, like having dictionaries or sets, right? So that's why it's important to know how they are working internally, and like what kind of time complexity you're going to get for different operations. So the usefulness of hashing comes from the problem of indexing. What is the problem of indexing? Imagine we have a lot of documents, you know. These documents can be anything. Like in our case, let's say they are phone numbers, and we want to create a phone book. So what kind of different indexing techniques we can use? So let's think of a very simple one. Let's start with the inefficient but easy to implement one. How would you implement that? You are given some phone numbers, and if you are working as a phone book, you need to support two operations. Or maybe three operations. One is addition of a new number, because people are going to buy new SIM cards, and then you need to add their numbers to your phone book. So the other one is deleted numbers, like, because some people are going to give up on their cell phones, or they are going to change numbers, so some numbers are going to get deleted. This is the second option, second operation that we should support. And the third operation that we should support is search. Like basically, given a name, we should find the number, or let's say if we are just talking about numbers, given a number, we should check whether it's part of the phone book or not. So, three operations that we should support: addition, deletion, and search. So, let's try to come up with a very simple solution. How we can do this with everything that we had learned so far? Like, can we use an array, for example? A little louder. We can use an array, right? So basically, every time a new phone number comes, we can add it to the end of the list, for example. Let's start with a simple approach. So let's say this is our array. What we are going to do is we are going to have a pointer to the first empty location in our phone book. And then whenever a new phone number comes, like the insertion operation is basically adding that number to here, right? Let's say the first is phone number 1, and this is phone number 2, this is phone number 3, this is phone number 4, and so on. So what is the cost of insertion with such an array? It's constant, right? Because we know exactly what slot is empty, and then we put the number over there. So insertion cost is good, it's all mine. How about deletion cost? Like, let's say they told us, okay, so P3 is not used anymore. OM, right, in the worst case, because we have to do the linear search to find where P3 is. And likewise, how about the search operation? Like for deletion, basically we are running the search, right? Obviously, this is OM too. So if we consider approach number 1, let's say here, array in incoming order. So this is our approach. And we have insertion, deletion, and search. So our insertion cost here is O1. Our deletion cost is ON, and our search cost is ON2. And for the deletion, like, we also, after finding the element, we have to apply a little trick. Since we want to keep all the existing ones on here, let's say we are deleting P3. Like, once we find P3 with the linear search, what we are going to do is we are going to write the latest element over P3. And then move our empty slot back by 1. Okay? So this is how we can keep it in the structure like this. Are you guys clear with the delete operation? Like we find it and then we get the last element and then we also update our first free spot pointer 1 back so that we can use that slot again. It becomes available because we make 1 deletion, right? Number of numbers in our phone book is going to be decreased by 1 after the deletion, that's why. Okay, any questions about this approach and the time complexity? It's clear, right? Okay, so let's say we are cool with increasing our insertion time, but we want to do search faster. What can we do?
We can keep an array in increasing order, so we can do binary search of it.
Yes. Let's say we did this, and this time, like let's say their previous order was P1, P2, P4. Or let's say like they were P1, P4, P2 in the previous one. Now that we keep them in sorted manner, then they are going to be like for this scenario, it's going to be P1, P2, P4. So, this time, when I'm inserting an element, what am I supposed to do? Since things are in the sorted manner, what's going to be the time complexity to find the right spot for the upcoming phone number? All again, right? Because we can just apply binary search. And after I find, for example, I'm trying to insert P3 and then after that I found this spot. What am I supposed to do next? We need to shift everything that is on the right one to the right so that we are going to have this empty slot available for the new number, right? So what is going to be the insertion time in the worst case? O n, right? Like what if every time we keep getting numbers that are smaller and smaller? So in that case, like everything has to be moved by 1, right? Every insertion operation. So in the worst case, like array insorted order approach will have O n of insertion cost, right? How about deletion? Again, in order to find the right spot, we can use binary search, right? In log n time, we can find the spot. But after that, we cannot just bring the last element and override because it's gonna disturb the order, right? So that's why what we are supposed to do is the reverse of what we had done for inserting, right? Like after we find the right spot for the element that we are supposed to delete, everything that is on the right of that needs to be shifted left by 1, right? So what's going to be my time complexity then? Order of n. Okay, so now like why are we getting these O n costs? There has to be some benefit, right? If everything is worse, why are we talking about this? How about the search operation? Log n, right? So now we get the benefit of keeping things in order to have more efficient search operation. All right. So, like depending on our application, if it's going to be search heavy, then obviously we would choose array in sorted order approach. Otherwise, we would go with array in incoming order. Okay. So the question is, can we do better than that? So once we ask these questions, usually the answer is yes. Like there are very few cases. Once you think about there is no better way. I mean, obviously there are such cases. But in most of the time, there are better solutions, more efficient solutions. So, for this problem, now we actually come to the point of when hashing is going to be super useful. So, the idea of hashing is that, before actually we can consider one more approach, which is direct indexing. Meaning, let's say these are phone numbers, right? And how many digits do phone numbers have in Ethiopia? 10? Including the 0 at the beginning or no? Including the 0. So we don't need 0, it's 0 for everybody, right? Let's say 9. Is it always starting with 9? Okay, then we don't have to consider that one either. So now we are left 8 digits, right? So 8 digits means... So, how many different possibilities? Like basically we have 100 million different possibilities, right? Is 100 million big enough that we cannot take an array that long? It's not, right? I mean, we should be able to get a 100 million array. Like, how much memory it's going to take? Let's say we are getting integers. We are going to multiply it by 4. Like, it's going to be 400 million bytes. Delete 3 zeros, it's going to be 400,000 kilobytes. Delete 3 more zeros, it's going to be 400 megabytes. It's not that much. So, if we are able to get this big of an array, what can we do?
We can put a 1 or a 0 at that specific spot when the 4 number exists.
Yes, so basically, instead of having this little arrays, we are going to have this relatively gigantic array, whose length is going to be 100 million. And whenever a number comes in, let's say we want to insert P1, we are going to go to the P1 cell in the array, and then we are going to put 1 inside, indicating that that number do exist. And after that we get P2, we are going to go to P2 and say, we are going to put 1 in it, and then we are going to do the same for P4. Alright, so, let's call this direct indexing. Indexing. What is going to be my insertion cost this time? Constant, right? O1. How about deletion cost? Again, I'm going to go to that cell and then make 1 0, right? This is O1 too. How about my search cost? Again, O of 1. I just go to that cell and check whether it's 1 or 0, right? So, I mean, this is kind of perfect scenario, right? We can do everything in the constant time. All the operations that we are trying to support. Then why bother after this point?
Because of memory.
Because of memory, right? Like, in order to be able to apply this to Ethiopian phone numbers, we have to apply 2 tricks, right? We basically got rid of the first 2 digits. Without that, the memory need was going to be higher. And imagine, in different contexts, actually the range can be way higher, right? And like if we are talking about different x's for problem C yesterday, the range was up to 10 to 12, right? And there is no way we can get that much of a memory. Like maybe you can do that Google, but obviously not in your local computer, so. All right, yes. So this is when the hashing becomes handy. Because if we are able to use direct indexing, all the operations are supported in constant time. That's perfect case for us, but it has this huge memory requirement. Maybe it's better to add this memory requirement here as MQ. So for array in incoming order, what is our memory requirement? How big of an array we need? ON, right? And for array in sorted order, it's the same. How about direct indexing? Let's say like R represents range. Let's put a note here. We are getting the range. Like the range of the elements, right? We need to get that big of an array so that we can use direct indexing approach. When this is not feasible, there is a trick that we can use. Because like depending on how many numbers you are trying to index, like as you see in these 2 cases, obviously you are going to need that much of a memory, right? I mean, without that, it's how are you going to do that if you don't keep track of things, whether they exist or not? So, ON memory is kind of needed, right? But at the same time, OR might not be acceptable for some applications. Like, do you guys have, for example, national ID? Maybe not? Okay. Like, imagine, let's say you have national ID with 12 digits. In that case, this wouldn't be enough, right? And how many people do you have in the country? Like, you have around 100 people. 100 million people, right? Like, actually, N is in the order of 100 million, or like in the order of 10 to the 8, and the range of the IDs, it's in the order of 10 to the 12. So, when there is such cases happening, hashing becomes very useful. So in hashing, what we are doing is, instead of going and placing things to the direct match of the cell, we take the hash of the value that we are trying to insert. And our hash function usually has a range as much as the memory we want. Let's say you want to use up to like L elements in your memory. You know, like you want to have memory of OL. So in that case, you need a hash function which is gonna return you values between 0 and L. And in order to have less conflict, because if we are doing this, it means we are gonna have some conflicts, right? Because what's the power of direct indexing? There is no conflict, right? So two different numbers will always go to two different cells. But when it comes to applying hashing, since we are basically making the range smaller, there will be a risk of conflict. Meaning, two different IDs after applying the hashing function can point to the same location. So then we will also have to work with this collision detection and collision resolving problems. Okay? So, let's do it with an example so that it's going to be clear for everybody. So what we do is like whenever P1 comes in, that we are going to insert it here. So we apply hashing function to P1. And then we get HP1, let's say. And after that, I go to my array here. My array's ranges, so H is a function. H range is from 0 to L. Meaning here my array is, so this time it's going to be shorter than this guy. So it has 0, 1, 2, L minus 1, like total L different cells. And after applying the hashing function, this gives me HP1, right? Then I go to HP1 cell here and place P1 inside. So, assuming we are not going to have any collisions, because right now we didn't see collision handling yet, but we are going to come to that in a moment. What is going to be my insertion cost with this algorithm? It's going to be constant time, right? Because, I mean, obviously it depends on implementation of your hash function, but you're not going to pick a very complicated function for that, like, because you're going to be calling it many times. And usually, like, the popular hash functions are taking the mode of the number with some large primes. Because this way you have less conflicts. Otherwise, like, if you're taking the mode operation and if your number is not prime, then you have more risk of getting conflicts. That's why they are usually choosing prime numbers. So if you remember some of the Code Forces contests, when they want you to report the results, they ask you, hey, take the modulo of a very large number, and usually if you check that number is prime. That's why they do it that way. Okay, so our insertion cost is O1. How about deletion cost?
O1.
It's also O1, right? Pretty straightforward operation. We just apply the hash function to choose the right cell, and then we just go there and delete it, assuming there is no collision, because we are going to get back to how to handle collision. How about search? Huh? O1, right? I mean, again, the same thing. We just go to that cell instead of inserting or removing. We just check the value inside in it. Search is O1, and the memory requirement here is L. So that's another power of hashing. Basically, independent from the range of the elements, like you can, you know how much memory you are going to use exactly. But obviously the length of the memory is important, right? If you get a very little array, you're going to have a lot of conflicts. If you get a very large array, you're not going to have conflicts, but you are going to be wasting some memory. So there is a trade-off when you are choosing L in comparison to R. Like R is the range of the values that come inside, like the phone numbers range in this example. And L is the length of our array, hashing array, plus the range of the hash function. Because the hash function has to return something between 0 and L minus 1 so that anytime I can make sure it's going to be in this place. Okay? So that's why, like in that case, for example, the proper hash function can be like getting mod of L. Because this way I guarantee that the numbers that are returned by the hash function are going to be between 0 and L minus 1. Right? Okay, so any questions up to this point? So now I want to speak more about how we should choose this L value. So now let's consider some trade-offs between L, R, and M. Sorry, L, R, and N. N is my number of elements. N is the range of the hashing function, and R is the total range of these numbers. So, do you guys think that like there is a close relationship between L and R? Or is it more important to compare L and N? Like we can think of an extreme case to understand which of this relationship is more important. Let's say the range is from 1 to 1 trillion, but I'm dealing with only 2 elements. How big of a memory you should get? Should it be close to 2 or should it be close to 1 trillion? Close to 2, right? So which relation is more important then? L and N, right? So now let's get rid of this L. And now let's think about it. So let's say on average, now we are going to do average case analysis, not worst case analysis, not best case analysis. We are going to do average case analysis here. So, what is the probability of getting a conflict given L and N when I'm inserting the element N, when I'm inserting the last element?
If it's repeated.
What's that?
If it's repeated.
If it is?
Repeated.
If it is repeated. What do you mean by repeated?
The numbers.
Oh, I mean, if they get the same hash value, then they are going to have conflict. That's right. But like, I'm asking like, what is the probability? It shouldn't depend on whether it is repeated or
1
not.
over L.
What's that?
1 over L.
1 over N.
L.
1 over L.
Yeah.
So let's think about it. Why do you think it's 1 over L?
A number's probability of, for
But this is
example,
independent from N, you know that, right? So basically your formula says whether we have 2 elements or whether we have 100 million elements, the probability of getting a conflict is always the same.
Okay, so I was thinking about if we choose the L, and random numbers probability of the mod of L is same with the other numbers probability of the L is.
But we are
1 over L.
calculating the conflict probability. How many different numbers are there in your array? That has to be a multiplier for this. Like as I said, like the probability we find has to be dependent on both N and L. If you say it's 1 over L, it means the conflict probability is not affected by how many elements I'm inserting in this. This doesn't make sense.
Well, I thought 2 elements conflict probability. Okay. I thought only 2 elements conflict probability.
Even if you consider 2 elements conflict probability, what I'm saying is, by your formula, 2 elements conflict probability is not affected by a number of elements that we are inserting to the array. And this is not true. Like let's say if I'm inserting 2 elements here, and L is 5, so you say the probability of getting a conflict is 1 over 5. What if I am inserting like 100 million elements, and my L is still 5? So is it 1 over 5? I think it's 100%. Yes?
L over N?
L over N. So now let's think about this one. So, what do you expect? Do you expect our conflict probability to go up once I have larger space or not? Like with this formula, if I get a bigger array, then the conflict probability is increasing. Are you able to follow? And does this make sense?
No.
It doesn't make sense, right? Okay. So,
It should be
N over L.
N over L. Yes.
And
N over L.
what I was talking about is if N is 2, then it is going to be 2 over L, but and it is actually N minus 1 over L.
Okay, I mean, almost. Okay, I see your point. You were focusing on only one
Yeah.
specific case, but like we are considering the general case. But I think everybody's on the same page now, right? Okay, so now we are clear that our. So let's think about it. N over L. If I have more numbers, my conflict probability is increasing, right? Makes sense. If I have larger space, then my conflict probability is decreasing, right? And on average case, let's say if I have a space that is as big as number of elements, then when I'm inserting the last element, this is going to 1, right? Or like let's say if I'm inserting 1, like n plus 1 element. It's gonna like that. This might be n minus 1 actually, right?
Yes.
If
There is one element. it is
yes,
zero.
to be completely correct. So like basically, still like we understand the relationship between the space that we are getting from the memory and number of elements that we are inserting, right? So based on how many elements are coming, you can choose an L and target an expected collision ratio. Let's say if we are inserting 100 million elements and we get an array of 20 million, then obviously we know that there is going to be a lot of collision, right? So this is not going to be desirable. So usually you try to pick L that is slightly larger than N, so that you're going to decrease the risk of getting collisions. Okay? So any questions up to this point? Okay, so now we are going to start talking about how we can handle the collision case. So the collision happens when we are inserting an element to a cell which was occupied by a previous element. So let's say the HP1 pointed here for P1. And then now I want to insert P3. And then the hash function coincidentally gave me the same hash value. This might happen because the normal range is bigger, but once we try to map it into a smaller range, obviously there are going to be some conflicts. So now once this happens, we go to this cell and we want to insert P3 here, but it is already occupied by P1. What can we do? So the first thing we can do is, instead of using this as an array, we can basically start linked list from these cells. And from HP1, first we were pointing to P1. And now I can add P3 to the beginning of here or end of this linked list. So now I can insert P3 here. So since this is a linked list now, in the insertion operation, if you want to keep the cost low, you can always insert to the beginning, right? Because otherwise you have to go till the end. But when it comes to searching this time, how is the searching going to be affected by this?
You have to iterate over.
We have to iterate over this linked list, right? What is the worst case complexity?
O(n).
Everything is going to come to the same. But worst case, it's not very likely to happen under such circumstances. What is average complexity? That's why for hashing we more focus on the average cases. How many elements do we expect to have in this linked list after placing n elements into L cells?
One.
One, independent from n and L.
N over L.
N over L? Yes. Because we are putting n elements into L spaces. Obviously, for each spot we are going to have n over L. Because we are going to multiply it with number of cells, which is L, to get n. Right? Okay, so we know that the length of this list is n over L. Then how is it going to affect my insertion, deletion, and search costs? So for insertion, we can say we are going to always insert to the beginning. What is going to be my insertion cost?
Constant.
O1, right? So it's right now we are doing hashing. So like let's call this one perfect hashing. No conflicts. No collisions. And now we have hashing with collisions. So our insertion cost is O1. How about our deletion cost? Because I'm going to go over this list, right? Even if I go to the middle of it, we are talking about asymptotic complexity. So that's why it's going to be n over L, right? Or usually, like in hashing, since this ratio is very important, like it comes up again and again, they usually call this alpha. Like alpha is the ratio of your memory and the range that you are mapping into your memory. So like this is n over L. So in that case, we can just put alpha over here. How about search cost?
What?
What's that? O alpha, it's the same, right? And what is our memory requirement?
O(L) times n?
O-N.
Or O(n).
Actually, it's more like OL plus N,
Yeah.
right? If n is bigger, then it's gonna dominate. That's why. Like we basically have one location for each of the elements in these linked lists. That's why. Okay, so this is one way of solving collisions. Hashing with collision, and our solution is linked list here, or with list, let's say. Hashing with collision. List. Okay, so that's one technique we can use. There are some other techniques we can use. So instead of having a list here, actually if we know that there are going to be a lot of empty spaces in this array, we just unluckily get this conflict, what we can do is, we can look for the next cell. Like we can basically keep looking for the next free cell, you know? Because I know that whenever I am looking for this element, the hash function is going to send me to the same place, right? So I'm going to come to HP1 again. Like let's say P1 was inserted here. So now when I'm inserting P3, I come here for HP1 and then I see that this is occupied. Then what I do is, I keep going to the right until I find an empty slot so that I can place P3. Okay? So in this example here, since the next one is empty, so I can place P3 over here directly. So, let's think about it. If I handle conflict resolution this way, what would be my insertion cost?
First
What's that?
first
O?
O-N.
O-N. We are not talking about the worst case. O of alpha, do you say, I think. And is this the case? Are we sure about that? Because that number of elements, like n over L elements, are going to hit to this cell, right? And they are going to be occupied, they are going to come over here. So once the last one comes in, how many elements I'm going to be looking here? N over L, right? So that's correct. Now we have hashing with collision with linear probing. So the operation we are doing here is called probing, because we couldn't find an element here, we couldn't find an empty slot at the first place we looked. So now we need to look for an empty spot. So we keep going to the right. And we are going linearly, you know, like we always looking to the next cell, and then to the next cell, to the next cell. So that's why it is called linear probing, okay? So did you guys get the idea for insertion? We go to that cell, if it is occupied, we look at the next cell. If that's occupied too, we look at the next cell, until we find an empty slot. And now you can also think of this, obviously it's going to be this way, like after you reach the L-1, you're going to continue looking from the first one. Okay, so you can think of this circle. Alright, so our insertion cost is O alpha now. How about our deletion cost? Actually, this shouldn't be O like that. The average case was annotated with another letter, right? Theta? Okay. I don't know how good of a theta this is, but I mean, you guys get the point, so. Okay, so how are we going to do deletion this time? So the hash function is going to point us to the same place, right? And if this is the number that we are trying to delete, we can delete this, right? So if we delete it, but we are going to deceive the search algorithm. So that's why if we are using linear probing, we don't delete things with the hard delete, but we mark them as deleted. The reason is, let's say we are looking for P3, okay? So I wanted to delete P1. I come here and then I say, oh, this is P1, I deleted this. And now I'm looking for P3. The search operation is called with P3. How am I going to do the search? I'm going to give P3 to my hashing function. And the hashing function is going to tell me go to HP1. And I come to HP1, oh, it's empty. It means P3 cannot exist. And then I am under the false impression that P3 does not exist. But indeed it does exist. So in order to avoid this case, when we are deleting P1, we do not delete it physically. P1 stays here. And then we put a mark on it to indicate that P1 does not exist anymore. Okay? So this way, when I'm looking for P3, I come to this cell. And then I check, is this P3? No, but this is occupied, so I need to look for the next one. Is this P3? Yes. Now I can delete this. And I am not deleting with the hard way, because otherwise if there are some elements here with conflict, they are not going to be accessible by the search operation. Okay? So, this way, what is going to be my cost of delete?
O alpha.
O alpha. How about search?
O alpha.
It's the same, right? I come here and then I need to go until I find a real empty slot to make sure that number doesn't exist. Because in case of conflict, I should keep going. But there is one thing which is an important one. So, do I actually have to keep going as long as those cells are occupied? Actually not. The reason is, yes, some of them came here because of the collision. But let's say HP4 is, we don't need this anymore. HP2, and then HP2 is here. And P4 is here. So right now, let's say I am looking for a place for P5. I want to insert P5. No, let's say next one. Okay. Yeah, actually, once, as long as it is occupied, you should be checking. So I was thinking that, like, what if the hash function of that element is not equal to yours? So in that case, you should still continue looking, because imagine the case like I inserted P1 and then I inserted P3 and then I inserted P4 and now I am trying to insert P5 and like its value is HP1. So now I come here, it's occupied. I go to the next cell, it's occupied. I go to the next cell, it's occupied. So I'm going to insert P5 over here. Right? So even if P4 has a different hash function, hash value, I have to continue my search. Because there could have been a conflict before, that's why I have to continue my search. So, meaning my search cost is going to be O alpha as well. How about the memory requirement?
O alpha.
Because this time there is no way I'm starting a linked list or anything, right? But assuming L is greater than N, it is OL. Because otherwise, where are we going to put the extra elements, right? Okay. So, any questions about linear probing? Are you guys clear? Yes.
When we are inserting an element, let's say we found the hash of the hash P1 and we go to the P1
Yes.
and we see it is deleted, but it is marked but not deleted. So we are replacing it with previous one.
Yes. So let's say right now. Okay, that's a very good question. So let's say now we want to insert deletion operation happened here, like delete P1. Let's say that P1 come here and then marked this one and then. So let's write the operation order clearly here. So first we inserted P1, and then we inserted P3, and then we inserted P4, and then we inserted P5. P1, P3, P4, P5. This is how it would look. And then let's say we delete P1. So what is going to happen is, it's going to look like this, right? And let's say now we are inserting HP6, which has the value of P1. So what is going to happen is we are going to go to HP1, right? And we are going to check, is this slot available for insertion or not? If it is deleted or if it is empty, then it means it's available for insertion. So then, I am going to insert P6 here. Because it's available. I mean, there is no point in keeping that delete mark like the grave of P1. We don't need that. So is everyone clear with this? Okay, is it clear, Murat?
Yep.
How you're gonna handle this case? Okay. So any other questions? Now we are clear with linear probing, right? So that's a good algorithm, but at the same time, because of this linear probing part, we can actually have a lot of collisions. So there are different forms of probing algorithms. Like another one is quadratic probing. Hashing with collision with quadratic probing. So, like basically here, what were we doing? After we get to the hash function value cell, if it is occupied, we keep checking cells one by one, right? And instead of doing this check one by one, with quadratic probing, what we are doing is, like first we obviously check the cell. Like hash value, let's say hash value plus square of 0. It's basically here, right? And then we check hash value plus square of 1. So we are going to be checking next this cell. And then we check hash value plus square of 2. Now we are checking like 1, 2, 3, 4. This cell. After that, I'm going to be checking HP plus 3 over 2. So do you see what's going on here? Instead of just looking the next element, in case of like having a lot of collisions, instead of putting them all in one place, we are separating them in our array. Like obviously we get the modulo of L in the end. So if it's too much out of here, then it's going to come back in here. Okay?
Does this make any difference than linear probing?
Yes. Because in the linear probing, if you have, like you can have some areas very collided and some areas more free. Like this way you are able to avoid that. I think in practice this is performing a little better than this one. But in terms of asymptotic time complexity, I don't think it's going to make any difference. It should still be the same. But like these are basically these different probing algorithms because in practice they see different results. That's why they use it. Okay, so like do you expect any changes in the insertion, deletion, and search? Like is it clear how we are going to execute the operation? It's just like the way that we are looking at the next cell, it is changing. In the previous one it was linear. And this time like I'm going to calculate the new index by getting the square of the displacement. Okay? And my complexities are going to be the same. Alpha, alpha, and alpha. And finally, so still like in this one, like in linear probing we use +1 to look at the next cell. And here we use plus I square, or let's say for this we use plus, and here we use I square. Still these are not very complicated functions, like meaning the collision, the collided areas can still be dense. So another approach they are using for collision resolution is having another hash function. So basically, instead of calculating our hash value like this, what we do is like HV plus HV2 times 1. HV plus HV2 times 2. HV plus HV2 times 3. So what we are doing is like we introduced another hash function now. And in order to find, like in case of collision, the next cell we are looking is multiplication of the next cell with the displacement. So if we are checking just the next cell, then HV plus HV2. If we are checking like next, then HV plus 2 times HV2. So by using hash function, again, like I think in practice they observe better results. That's why. That's another way of doing the probing. So finally we have hashing with collision with new hash function probing, let's say. And do we expect any changes in the asymptotic time complexity? It's going to be the same, right?
these perform better in the practice because of the data is so similar. That's why.
Like it's well separated with the help of the second function. Like instead of checking the same places in the same area, like having a collision over here a lot and having a lot of free cells over here, like it helps you to distribute them more evenly to the available array. That's why. Okay. So any questions up to this point so far? So which data structures that we were using in our preferred languages actually make use of hashing or can make use of hashing?
On C# dictionary.
Dictionary, right? Or map, like in which basically we have keys and values. So depending on which one we are talking about, there can be multiple values for the same key. But the idea is it's not going to have duplicate keys at all. Like it has unique keys, right, in the dictionary. Or is there any other data structure that can make use of this?
Set.
Set, right? Like set is a simplistic form of dictionary in case of not having any values. If you're just talking about keys and checking existence of some keys, then set is a super handy data structure, and it is exactly like many implementations of sets depend on hashing because of these good time complexities. Like here, our time complexity looks alpha, right? But what if alpha is constant? Because that's the ratio of your array. Like what was alpha? I think I deleted
N
the
over L.
definition. This is n over L. Like meaning if you get very large array, it's going to be constant. If your array is like half of what it is, then still it's O2, you know? If it's like 1/3 of it, still O3. Like it's very close to constant. It's not close to log n, you know? Okay, so any questions up to this point so far? Is hashing clear? Why we need it and how it can be helpful making these operations more efficient with less memory usage? Okay, cool. So now let's start with the homework. Please do check the implementation of dictionary and set in your preferred language and see what kind of different implementations it can support. Like for example, in C++ you have unordered map, ordered map, which give you different time complexities. Or in Java, like you have hash set, you have tree set, which gives you different implementation. Because in the tree set, they also keep things in order. It's more like ordered map. So that's why like you get log n time complexity. So please do spend maybe like 10 minutes right now on your computer and understand the internal dynamics of these two very handy data structures we use quite often. Okay? Thank you very much. That concludes our lecture today.